These test tubes sitting in the hood contain hydroxides of aluminum and beryllium.
The only thing that remains is to prepare the samples for AMS analyses. Our first goal was to precipitate the beryllium and aluminum from the liquid solutions in which they are currently dissolved. Those solutions are now acidic. Both beryllium and aluminum are soluble at both low and high pH, but have solubility minima at pH around 8. We'll exploit this property to isolate these elements as hydroxide gels. The goal of this process is to slowly titrate each solution up to pH 8, but not to go higher. At that point, the beryllium and aluminum will both precipitate as gels, although they really won't be visible in the liquid. We verified that it is clean of beryllium-10 and aluminum-26, as well as other contaminants that might inhibit AMS performance. The setup for precipitating hydroxide gels is fairly simple. We start by placing the methyl red indicator in a spill tray, along with ammonium hydroxide, 30% concentration. Both of these are in dropper bottles. Next to those, we place a waste beaker so that we can dispose of waste as we decant. We also have a squirt bottle of distilled water, milliQ water, that we use to rinse the samples. And we place a vortexer for mixing in the hood. You'll see the hot plate out to the side. That will eventually be used for drying off the samples once we have precipitated the hydroxide gels. And of course, in the background is a test tube rack with 2 lines of sample tubes. The orange tape indicates the aluminum samples, and the blue tape in the background indicates the beryllium samples. Methyl red remains red at acidic pHs and turns yellow-green between pH 6 and pH 7. For each sample, we begin by adding 1 drop of methyl red. We then titrate using a dropper bottle of ammonium hydroxide, a base, mixing after each addition. When the color changes, we know that we've reached a pH of about 7. We add 1 more drop of the base, which is to bring the pH to about 8. At this point, the beryllium and aluminum are in hydroxide forms in their respective tubes. We centrifuge the samples to condense this gel at the bottom of the tube after a strong vortexing. Because all the samples have the same amount of beryllium and are free of impurities, all the beryllium gels should be clear and about the same size. The aluminum gels can vary greatly in size depending on how much native aluminum was in the quartz. Once the samples have been centrifuged, we pour off the liquid carefully, leaving the gel behind. We then add pure milliQ water, we vortex the gel, we centrifuge it again, and we pour off the liquid 1 more time. This washing step cleans the samples of any lingering methyl red as well as alkali metals, which remain in the liquid phase. The last step is to dry the gels, which drives off all excess moisture. We do this slowly over the span of several days, beginning at a low temperature. We do it in clean air fume hoods to keep the gels clean. This slow, low temperature dry off causes the gel to slowly pull away from the sides of the tube and form a single coherent tiny pellet about the size of a flea. In the next video, we'll describe the last part of the process, preparing these pellets for the accelerator analysis. Let's recap. The goal of this process is to recover and purify beryllium and aluminum from the acidic liquid. We slowly titrate the solution for each sample to pH 8, at which pH beryllium and aluminum both precipitate as hydroxide gels. We use methyl red, a liquid pH indicator, because it turns green-yellow at pH 7. To do this titration, we use a dropper bottle of ammonium hydroxide, mixing after each addition. After the color changes at pH 7, 1 more drop of base brings the sample to pH 8. After all the samples have been precipitated, we centrifuge the tubes to condense the gel at the bottom of each tube. We then pour off the liquid carefully, leaving the gel behind. We wash the sample with pure milliQ water, vortex, centrifuge again, and pour off the liquid. The washing cleans the sample of lingering methyl red as well as alkali metals. We then dry the gels slowly over several days at low temperatures, causing the gel to slowly pull away from the sides of the tube and form a single, coherent, tiny pellet.